Hi everyone, my name is Nasim and I'll be presenting our paper End-to-End Phase Field Model Discovery, combining experimentation, crowdsourcing, simulation, and learning. In this work, we focus on scientific discovery of physics models. Physics models are, of course, important because they enhance our understanding of the physical world and lead to innovation of new technologies. For learning new physics models, we start with data that comes from controlled laboratory experiments and natural observations. This can include sensor readings, videos, satellite images, etc. Usually, these data are big in size, high resolution, and noisy. At the end of this pipeline, we get new physics knowledge, such as conservation laws, laws of motion, etc. The intermediate steps in between this data and the physics model consist of manual processing, such as annotation and denoising of raw data, model learning from annotated data, which can involve black box neural networks and partial differential solvers, and qualitative testing of the physics models through simulation and visualization of the model outputs. Manual annotation and denoising for high volume, high resolution data requires huge manual effort and hinders thorough analysis. The learned models needs to obey the prior known physics laws, which are often not the case. And researchers need to have easy interface to simulate and visualize the physics models to gain new insights. To accelerate the current physics model discovery pipeline, we need an integrated framework where all these operations can be done easily in a single place. With this state in mind, we present our AI-driven integrated framework named Phase Field Lab, which can assist in learning phase field physics models from experimental data. Phase Field Lab framework provides easy interface to pixel-wise annotate video data and learn phase field models from data with expert in the loop, and also simulate and visualize phase field model outputs easily with varying initial conditions. Our phase field lab is motivated by the need of AI-driven search for strong materials. Designing strong materials that can sustain extremely high temperature and heavy radiation is important for energy applications, such as nuclear reactors. To design such materials, understanding material behavior and degradation is essential. In the figure, you can see an experimental setup in the Argonne National Lab in the USA, where scientists perform in situ experiments to understand behavior of nano-sized defects in irradiated materials. Our phase field lab provides an integrated framework to analyze these in situ experiment videos. Uh, phase field lab contains three modules for interactive annotation, phase field model learning, and simulation visualization. The interactive annotation module takes an experimental video frame and then outputs a pixel-wise annotation of material defect in the frame. To do so, we first segment the original video frame into superpixels using simple linear iterative clustering. A human user then can select the superpixels corresponding to the material defect by clicking and erasing the original image through an interactive interface. In this way of superpixel clustering and clicking erasing, we can easily obtain very accurate pixel annotation of these video frames in minutes. For example, a 1000 by 1000 resolution image can be pixel annotated in this way in less than 6 minutes. This actually results in the reduced manual effort. The second module of our phase field lab, the learning model, takes as input three things: in situ experiment video, partial annotation of this video, and expert given possible range of the phase field model parameters. The output of this learning module is two things. First is the tracking of nano-sized void defects as seen in the video, and second is the set of phase field model parameters that can describe the dynamics of this nanovoid defect. The learning module combines two neural networks. One, the recognition net, and two, the neural differential equation net. The recognition net extracts phase field variables from raw video frames, and while the neural differential equation net embeds the phase field model equations in the learning and simulates the evolution of the extracted phase field variables. When the two networks are trained perfectly, the simulation outputs, available annotations, and recognition outputs should match perfectly, and the phase field model parameter values should be within expert given range. The loss function in our neural network penalizes the difference among simulation, annotation, and recognition outputs, also has the regularization term for violating expert given range constraints. The last module of our phase field lab, the simulation and visualization module, use finite difference approximation and forward Euler merging to solve partial differential equation of the phase field models. The intermediate steps of the solution are saved and rendered as video to see a simulation of the system evolution, starting from any given phase field model parameters and initial system state. We evaluated our phase field lab on two modules, the annotation module and learning module. On evaluation, we found that our annotation module can reduce the annotation times for different shape material defects by 50 to 75% compared to the baseline. The resulting annotations are also more accurate compared to the baseline. The large effect size, Cohen's d value in all measured metrics indicate that the phase field lab offers significant improvement in annotation thus compared to the baseline. On evaluation, our learning module provides very accurate tracking of nanovoid defects and also simulation output that matches closely with the ground truth. The baseline near-deep model provides similar accuracy as well in both tracking and simulation. However, the baseline models violate expert-given range constraints, while phase field lab models always satisfy this range constraint and thus yield more practical phase models. Our phase field lab has been already deployed in the analysis of in situ radiation videos in the real world. Previously, manual analysis of even a small 10-minute video took around 3.75 months for a graduate student worker due to very high resolution and high frame rate of these videos. With our phase field lab framework, this can be now accomplished in a day. As a result, the video analysis process has been accelerated greatly. Using our phase field lab framework, we are able to discover a new size fluctuation property of nanosize void defect in materials under irradiation. Previously, the size change of these nanovoid defects were assumed to be monotonically increasing or decreasing. However, we found that the size change mimics a random work-like pattern. Later, this discovery was verified by further manual measurements and physics simulations. In summary, our phase field lab provides an integrated framework for experimental video analysis and learn new physics knowledge. Phase field lab can reduce video annotation times by 50 to 75% and accelerate the scientific discovery workflow. Our framework has already shown real-world impact in the discovery of size fluctuation property of nanovoid defects in irradiated materials. If you have any questions, please let us know through email. Thank you all for your time.